The collective of theoretical computation had been studying alien species for more than 11,000 cycles. In all that time, they had seen many things. They had seen civilizations build machines that could think faster than light could travel. They had seen species create computers from living crystals and fold space itself into processing units. They had cataloged the programming methods of over 800 spacefaring races. They believed they had seen everything there was to see. Then a probe returned from a small blue planet orbiting a yellow star, and everything changed. Doctor was a senior researcher at the collective. Their body was made of crystalline structures that could process information at speeds no biological mind could match. They had spent 3,000 cycles studying the code of alien civilizations. They had written papers that were required reading at universities across 17 star systems. They were considered one of the greatest minds in computational theory. When the probe's data first arrived, almost ignored it. The initial report was not promising. The planet, called Earth by its inhabitants, was home to a species called humans. Their technology was primitive by galactic standards. Their computers ran on silicon chips and electrical impulses. They stored data on magnetic disks that would degrade within decades. Their processing units generated so much heat that they needed fans to keep them cool. Fans, like a child's toy. The collective's assessment classified Earth's technology as developmental stage. The report suggested the humans were unlikely to produce anything of value to computational theory. Most researchers would have filed the data away and moved on to more interesting subjects. But was thorough. They always reviewed the raw data, even when the initial reports seemed uninteresting. So they opened the first code sample from Earth. It was a simple program, a pathfinding algorithm, the kind used to help a machine find the shortest route between 2 points. Every civilization developed such algorithms. The collective had thousands of them in their archives. This one was different. Stared at the code for a long time. Then they ran it through their analysis systems. Then they stared some more. The algorithm worked in a way no civilization in the collective's database had ever conceived. It did not use quantum parallelism. It did not fold dimensions. It did not leverage any of the advanced techniques that spacefaring races typically employed. Instead, it was simple, elegant. It accomplished in 40 lines what the standard solution required 600 lines to achieve. And more than that, it was readable. A junior researcher could look at this code and understand exactly what it did within moments. Requested more samples. The data archives had thousands of programs from Earth. They began reviewing them one by one. Then they stopped sleeping. Then they stopped attending symposiums. Their colleagues grew concerned. Some thought they might be malfunctioning. One day called an emergency meeting of the senior researchers. They projected a piece of human code onto the conference hall's main display. It was something called a recursive lambda expression, a way of making a function that could call itself while remaining remarkably compact. "Have any of you ever seen anything like this?" asked. The room was silent. No one had. Dr. Null, who studied how different species approached problem-solving, leaned forward in her seat. "Where did this come from?" "A planet called Earth," said. "Their technology is primitive. Their hardware is laughable. They have no quantum processors, no dimensional computing, no neural networks made of light. They write their code by pressing physical buttons with their appendages." "That's impossible," said Dr. Vex, head of the Advanced Algorithms Division. "No civilization at that technological level could produce code this elegant." And yet they did. Displayed more samples, sorting algorithms, data structures, compression methods. Each one was different from anything in the collective's archives. Each one was simpler, cleaner, more beautiful than it had any right to be. The researchers began talking over each other. Some demanded to see the raw data. Others questioned whether the probe had made an error. A few sat in stunned silence, trying to process what they were seeing. "I propose," said, raising their voice above the noise, That we form a dedicated study group. I want to understand how these humans think. I want to know how a species with such limited tools created such remarkable solutions. The vote was unanimous. The Human Code Study Group was established that same day. Over the following cycles, researchers from 17 different species joined the group. They analyzed thousands of human programs. They studied human mathematics and human logic. They learned about human history and human biology. They tried to understand how these strange creatures, with their short lives and limited minds, had developed approaches to computation that no one else in the galaxy had ever imagined. The answers they found would change everything the collective thought they knew about the nature of intelligence and the art of writing code. Part 2. The Paradox of Constraint. The Human Code Study Group grew quickly. Within a few cycles, it had become one of the largest research initiatives in the collective's history. Over 300 specialists from 17 species devoted themselves to understanding the strange elegance of human programming. They built translation systems to convert human languages into forms they could understand. They created simulations of human computers so they could run human code directly. They studied everything they could find about how humans thought and lived. What they discovered was a paradox. Human programmers operated under brutal limitations. Their biological minds could only hold a handful of concepts in active memory at any one time. Most humans could juggle about 7 things in their heads before they started making mistakes. They were measured in decades, not. A human who spent their entire life studying programming would only have about 50 years of productive work before their minds began to slow. And their tools were worse. They had no direct neural interface with their machines. They could not simply think their code into existence. Instead, they communicated with their computers through physical keyboards, pressing buttons with their fingers in sequences that represented letters and symbols. It was like watching someone try to paint a masterpiece by throwing rocks at a canvas. The researchers were baffled. How could a species working under such constraints produce anything worthwhile? The answer, when they finally understood it, was profound. Human limitations had forced them to develop elegance as a survival strategy. Dr. Null was the first to propose the theory. She had spent cycles studying human psychology and culture, trying to understand how they approached problems. One day, she called an emergency presentation for the entire study group. "Consider she began. When they encounter a difficult computational problem, what do? They add more processing nodes," someone answered. "They throw more power at the problem until it is solved." Exactly, and the crystalline hegemony. They build larger code architectures, self-modifying systems that require dedicated artificial intelligences to maintain. Correct. Now consider the humans. They cannot add more processing power because their hardware is fixed and limited. They cannot build sprawling code architectures because their minds cannot hold such complexity. So what do? She displayed a piece of human code on the screen. It was a function that sorted a list of numbers. It was 12 lines long. They write this. Tight, clean, simple. They solve the problem not by overwhelming it with resources, but by finding the most direct path to the answer. The room was quiet as the researchers considered her words. "But there is more," Null continued. "The humans have developed something truly remarkable. They call it documentation." She showed them examples. Humans wrote explanations alongside their code. They described what each function did. They explained why they made certain choices. They created guides so that other humans could understand their work. "Why would they do this?" she asked. "Other civilizations do not bother. If you have questions about a piece of code, you simply ask the programmer who wrote it." "But humans cannot do that," said slowly, understanding dawning, "because the programmer who wrote the code might be dead." "Exactly." Null's voice was soft. "Humans write code knowing they will die. They write programs knowing that others will need to maintain them. They optimize for comprehension because they cannot assume they will be present to explain their work. They create elegant solutions because brute force solutions would collapse under their own weight within a single human generation. She paused to let that sink in. The humans have developed entire philosophies around this concept. They have something called clean code, a set of principles for writing programs that are easy to read and understand. They debate endlessly about proper variable nomming, about how to organize their functions, about how to make their intentions clear. They do this because they must. Their survival as a technological species depends on it. Dr. Vex, who had initially doubted the significance of human code, was the first to speak. We have always assumed that immortality and infinite resources were prerequisites for advanced computation. The humans suggest the opposite might be true. Not just suggest, Null said. They prove it. Look at what they have accomplished with so little. Their constraints did not hold them back. Their constraints made them better. The implications spread through the collective like ripples in water. Researchers began studying human code not just out of curiosity, but to learn from it. Universities started offering courses on human programming philosophy. The principle of constraint-driven elegance became a topic of heated debate in academic circles. Some resisted the idea. They argued that human code was merely a curiosity, interesting but not truly superior. Others embraced it fully, rewriting their own programs using human techniques and finding that they worked better than anything they had created before. But one question remained unanswered. The humans did not know that anyone was watching them. They did not know that their code had sparked a revolution in galactic computational theory. They did not know that beings from across the stars were studying their work with something approaching reverence. Someone would have to tell them. The debate over first contact began almost immediately. Some argued that the humans should be left alone to develop naturally. Others said that a species of such obvious value deserved to know their place in the larger community of intelligent life. Made the final argument. The humans are already reaching outward, they said. They send signals into space. They launch probes. They will encounter other civilizations soon, whether we contact them or not. Would it not be better for their first contact to be with those who admire them? The vote was not unanimous, but it was decisive. A delegation would be sent to Earth. They would meet the humans, and they would tell them what their code had meant to the galaxy. Part 3. The student becomes the teacher. The delegation arrived on Earth quietly. Their ships were small and designed to avoid detection, masked as atmospheric phenomena that human instruments would dismiss as weather anomalies. First contact protocols normally required centuries of observation before direct engagement with a new species. But the Human Code Study Group had argued successfully that this case warranted an exception. The humans were already reaching outward. They had sent probes to the edges of their solar system. They had beamed signals into the void, hoping someone would hear. They were not a species content to stay on their single world. They would encounter other civilizations soon, probably within a few generations. Better, the study group argued, that their first contact be with those who appreciated them. Led the delegation. They had spent more time studying human code than anyone else in the collective. They had learned human languages, studied human customs, and practiced generating a physical form that humans would not find too disturbing. It was not easy. Its natural body was a lattice of crystalline structures that glowed with internal light. Humans, they had learned, found such appearances unsettling. The meeting was arranged through careful back channels. A message was sent to a human scientist whose work had particularly impressed the study group. Her name was Doctor, and she worked at a university in a country called Finland. She specialized in something called compiler optimization, a field that dealt with making programs run faster and more efficiently. Her paper on register allocation had solved a problem that had struggled with for 800 years. Doctor was told only that visitors wished to discuss her work. She agreed to meet them in a small conference room at her university. She expected corporate representatives, perhaps from one of the big technology companies. She did not expect what walked through the door. Had done their best to appear human. They had generated a body with 2 arms, 2 legs, and a face with the appropriate number of features. But the proportions were slightly wrong, the movements too smooth, and the eyes glowed faintly with an inner light that no human eyes possessed. Doctor stared for a long moment, then, to his surprise, she laughed. "Well," she said, "you are definitely not from." Explained, as gently as possible, who they were and why they had come. They told her about the collective and the study group. They described how human code had been analyzed and admired across multiple star systems. They explained that her paper on register allocation was now required reading at 17,000 institutions. Doctor listened. She asked questions. Sharp questions, probing questions, the kind of questions that had made her solutions so elegant in the first place. She wanted to know how they had found Earth. She wanted to know what other civilizations existed. She wanted to know the details of their computational systems and why human code was so different. Answered as best they could. They explained about quantum processors and dimensional folding and neural networks made of light. They described civilizations that had been building computers for millions of years. They tried to convey the scope of the galaxy and humanity's place within it. When they finished, Doctor was quiet for a long time. Then she laughed again. "You came all this way," she said, "because we are bad at this." Paused, their crystalline processes churning as they tried to understand. "I do not follow your meaning. We write clean code because if we do not, we will never figure out what we did 6 months later. We optimize because our machines are slow. We document because we will forget." She smiled. "You are telling me that our workarounds impressed a galactic civilization." "Your workarounds," said slowly, "have become required study at 17,000 institutions. Your limitations became your greatest innovation." Doctor considered this. She turned to her laptop, an old machine by human standards, its fan whirring softly as it worked. She pulled up a file and turned the screen so could see. It was a sorting algorithm. Simple, clean, 23 lines of code. She had written it for her students as an example of good programming practice. "This," she said, "this is what you traveled across the stars to see." Studied the code. It was beautiful, not because it was complex or powerful, but because it was neither of those things. It did exactly what it needed to do and nothing more. Every line had a purpose. Every choice made sense. "Yes," they said, "this is exactly what we came to see." Doctor leaned back in her chair. "Well," she said, "I suppose I should start charging tuition." The first contact was not announced to the world immediately. There were protocols to follow, governments to inform, preparations to make, but word spread through certain channels. Scientists, programmers, the people who understood what had happened and what it meant. Within a year, the first human students enrolled at collective institutions. Within 5 years, human programming philosophy had spread across the galaxy. The principle of elegant constraint revolutionized how civilizations approached computation. Beings who had built computers for millions of years studied the work of a species that had only been writing code for decades. The humans found it all very amusing. "We spent so long thinking we were behind," Doctor told during one of their many conversations. "We looked at our technology and felt embarrassed. Our computers were slow. Our code was simple. We thought advanced civilizations must have left us far in the dust. And instead, you tell us we were doing something right all along, not despite our limitations but because of them." She shook her head. "It is a lot to take in." "Your species has a gift," said. "You turn constraints into creativity. You find beauty in simplicity. You write code not just for machines but for each other." "We had to," she said. "We are only human." In the centuries that followed, human programming philosophy spread across the galaxy. The Galactic Standard Library, a collection of the best code from all known civilizations, grew to include thousands of human contributions. Researchers who had once dismissed Earth as primitive now traveled there to study at human universities. And somewhere in the archives of the collective, preserved for eternity, sat a 23-line sorting algorithm written by a professor from Finland. It was the first human code officially adopted into the Galactic Standard Library. It was not the fastest algorithm. It was not the most powerful, but it was clear and it was clean, and it did exactly what it needed to do. It was elegant. And that, the galaxy had learned, was worth more than all the processing power in the universe.